So now let's talk about a relatively simpler scheme to implement, and that is called equal gain combining. Remember in the last video when we were studying the maximal ratio combining, our system model was like this, that we have capital M branches where we have capital M receiving antennas, and all of those antennas get multiplied with a gain. These gains were complex numbers A1, A2 all the way to AM, and then because of the gain which for maximal ratio combining, these gains were designed such that they result in a maximum signal to noise ratio at the combiner output. So a relatively simpler scheme would be that all of these gains have unit magnitude. So that kind of a combining technique where all these gains have a unit magnitude is called equal gain combining. And please remember that even in equal gain combining, you must have to co-phase your received signal so that you can get some gain out of it. So in equal gain combining, your received signal would still be at the combiner output, would be equals to summation I equals 1 to M AI Ri plus summation I equals 1 to capital M AI Ni, where now the difference would be that magnitude AI mod would be equals to 1 for all branches. That would mean that your gamma sigma that is equals to summation I equals 1 to capital M AI Ri whole squared divided by summation I equals 1 to capital M AI squared N naught. Remember that was N total for maximal ratio combining as well. And now if this AI magnitude is 1 for all of these branches, then we know that is this gamma sigma is nothing but summation I equals 1 to capital M Ri whole squared divided by now this is 1, so this would give you M times N naught. So that is what your received signal would look like. And you can see that this gamma sigma is not the same as it was the case for the maximal ratio combining. For example, you cannot write that this gamma sigma is equals to summation I equals to 1 to M gamma I. This is not the case. And because this is not the case, you would not be able to make use of the MGF or the moment generating function approach to compute the probability of symbol error, average symbol error under different kinds of weighting. So MGF approach would not work, that would not be very beneficial. Secondly, what is important is it's really difficult, although it's simpler to implement, but it is difficult to analyze. And what it means is that it is difficult to compute what is the PDF of the gamma sigma in this case. In the literature, you can for 2 branch identically distributed Rayleigh fading, people have computed the closed form expression and tried to compute what are the results with that. But the important thing is that if you simulate the results for the symbol error probability and the outage probability, that means if your symbol error probability is equals to integral from 0 to infinity P S of gamma P gamma sigma of gamma d gamma, so your symbol error probability would be very close to what you get in the maximal ratio combining. So that is an important thing, that this equal gain combining is simpler to implement, and it gives you a symbol error probability which is very close to. People say that this is within 1 dB of the MRC or maximal ratio combining. So that is an important thing. So that's about it. What we want to discuss about the equal gain combining, and now we'll move on to a topic which is called transmitter diversity. So that was all in all of the combining techniques, that is selection combining, maximal ratio combining, equal gain combining. We talked about the receiver side diversity. Now let's talk about the transmitter diversity. So the transmitter diversity, you need to first assume whether or not you know the channel side information at the transmitting end. So let's assume CSI known at the transmitter. So if you know the channel side information at the transmitter, then you can so remember, so the model would now be different. So previously you had multiple receiving antenna at the receiving end. Now you would have multiple transmitting antenna. For example, if you have a 2-branch transmit diversity, so you would have an antenna 1, you would have an antenna 2, you may have only one receiving antenna. So these signals would combine over the air, they call it, right? So if so this is your receive signal, receive antenna RX. This is H1, that is a channel from this antenna to the receiving end. This is H2, which is the channel from the antenna 2 to the receiving antenna. And if you transmit the symbol simultaneously, these two symbols would combine in the air to give you a receive signal, that is that you get at the receiving end. So let me write down the expression. So one important thing is that the gains, you can have, of course, the signal that you're going to multiply. For example, let S of t is the signal that you want to transmit, right? And so we would suppose that the channel gain HI, so we are calling this Ri e to the power j theta I. So don't confuse this to be the received signal. So this is the channel gain Hi, that is equals to Ri e to the power j theta I. And if S of t is your transmitted signal, then your received signal R of t would be equals to summation I equals 1 to m, your channel gain, which is Ri e to the power j theta I, times your transmitted signal S of t. So that is your received signal. So now what you can do is you can multiply this this transmitted signal with a gain AI. So let me call this as HI. So this is your HI. So your received signal R of t can be written as, so if you multiply with the gain now, right? So if multiplication with a gain is carried out at the transmitting end, then your received signal would be summation I equals 1 to capital M, AI, which is the gain that you multiply with the signal that is transmitted from the first ith antenna, times HI times S of t. So that would be your received signal R of t. And now you can see that depending upon what gain you have assumed for this transmission, your received signal to noise ratio would improve compared to the individual transmission without the transmitter diversity. And probably you can see that if this AI, one important thing to note already is that this AI, because you are transmitting it is a gain at the transmitting side, so this cannot have an infinite amount of gain. That means that would result in an unfair comparison, because that is, if you multiply with a gain that is very high, that means you are transmitted power would increase a lot. So this important thing is summation I equals 1 to capital M AI squared must be equals to 1. That means these gains should not increase the transmit signal's power on average. So that we need to make sure, otherwise you would be comparing apples with oranges, and that would not be a fair comparison. So having said that, now let's assume that this AI, if this AI is equals to HI, your channel gain, divided by summation I equals 1 to capital M HI squared. Suppose that is your channel gain. If that is your channel gain, it is fairly straightforward to prove, and we would do that in a while, that it would result in a gain that is very similar to a maximal ratio combining. So if that is your AI, what do we mean by this? If that is your AI, your gamma sigma would be summation I equals 1 to capital M gamma I, because that is what you get with the maximal ratio combining, and that's what we want here as well, that your gamma sigma with the transmitter diversity, when you have the information about the channel at the transmitting end, that would be summation of all the individual branch SNRs. So let's try to see whether or not this is possible. So remember, your system model is that you have multiple antennas at the transmitting end. You have, prior to the transmission, you multiply with the gain AI, and that results in the received signal. So if you want to compute your gamma sigma for the transmitter diversity, when you have the channel knowledge, would be your whatever your received signal is R squared over N total. Again, you are assuming that the bandwidth times the TS product is equals to 1. So that is known, and we are not going to repeat that. So this would be equals to the signal power, that would be equals to summation I equals 1 to capital M AI times HI times S of T, which is your transmitted signal, whole squared, divided by summation I equals 1 to capital M AI squared times N naught, where you're assuming that you have the same power spectral density of the noise on each of these branches. And again, now you can see that you can make use of the Jensen's inequality here to prove what is your gamma sigma max. So let me write it down here. So summation I equals 1 to capital M AI HI S of T whole squared over summation I equals 1 to capital M AI squared, and let me bring N naught outside, is less than or equals to summation I equals 1 to capital M AI squared. That would be one term, and the rest of the terms you would combine. So the summation I equals 1 to capital M HI times S of T whole squared divided by N naught times summation I equals 1 to capital M AI squared. So that is what you get with the Jensen's inequality, and you can see that the maximum signal to noise ratio would be equals to when this inequality changes to an changes to an equality. So under that condition, your gamma sigma max would be equals to summation I equals 1 to capital M HI times SI of t whole squared divided by N naught. So remember, you have HI times SI of t is nothing but your, so this is your channel gain for the IS channel. SI of t is your transmitted signal, and combined together these two would be your received signal at the ith because of the transmission of the ith branch or of the ith antenna, and square of that would be your ES for the ith branch. So ES over N naught, that would be your gamma I. So this you can see right away that this is nothing but summation I equals 1 to capital M gamma I, and which value of the gain would bring you that, and that we already know. We wrote down here, said if AI is equals to HI over summation I equals 1 to capital M HI squared, if that is your AI, you would have, so this left hand side of this inequality and the right hand side of this inequality would be equal. So that is the value of the gain that brings you that gain which is equivalent to the maximal ratio combining. So the important thing is that even with the transmitter diversity, if you have the channel side information, then you can have a gamma sigma that is equals to summation I equals 1 to capital M gamma I. And again, in this analysis you would have seen the analysis is analogous to the analysis of the maximal ratio combining, and even it is analogous to the analysis of the array gain under AWGN channel. So that is what you get if you have the channel side information at the transmitting end. Now, if you don't have the channel side information at the transmitting end, then if you go symbol by symbol or time slot by time slot, then you would not get any array gain, you would not get any diversity gain whatsoever. However, there is a scheme called the Alamuthi scheme that was proposed by Alamuthi when he was working at Bell Labs, and he proposed that if we do the analysis over two symbols and we do the transmission in a manner that we make use of two symbols, then we can get some diversity gain even if we don't have the channel side information at the transmitting end. So that topic we would look into once we have seen the MIMO. So our next topic which we are going to start would be multiple input, multiple outputs transmissions. We will talk about the diversity gain there, we will talk about the multiplexing gain there, and then we will also talk about the transmitter diversity and the diversity gain when you don't have the channel side information at the transmitting end. And we would cover the Alamuthi scheme, and then we would time permitting extend that analysis to the blast architectures, the so-called space-time block codes or the blast architectures, which can give you a diversity gain of a significant diversity gain even if you don't have the channel side information at the transmitter. Thank you.